Good evening. Today we'll discuss about half cycle based DFT algorithm. In the last lecture, we have seen the full cycle DFT. We have solved problems on full cycle DFT also. We have seen that how full cycle DFT helps us in determining the fundamental components, the DC component, and also any harmonics which are present in a sampled data. The full cycle DFT requires samples of one full cycle of the signal. In today's class, we will see about half cycle window based DFT, and I hope that by the end of this lecture, you will be able to determine the fundamental components from a given sample of digital data of fault voltage and current signal using half cycle window based DFT algorithm. So I'll start with half cycle DFT, and then we will move on to a sample problem on half cycle DFT, and then we move on to comparison between half cycle DFT and full cycle DFT. So half cycle based DFT, it is also very similar to that of the previous method which we have seen, the full cycle based DFT. The only difference is that the input signal is divided into two equal length half cycles, and the DFT is applied to each of the half cycles separately. So normally we do employ it in our signal processing because it reduces the time taken for computing the peak values, the phases. So full cycle DFT uses samples of one cycle duration to estimate a phase, whereas half cycle DFT utilizes only half cycle samples. Let us suppose this is considered to be a complete full cycle, right, up to this time. So when you are doing with full cycle window based DFT, you do require all the samples of your full cycle. In this case, see how many samples are there. There are nearly 12 samples which are present. So you do require 12 samples which are equated to one full cycle window. Whereas in case of half cycle DFT, you do require only 6 samples. Any continuous 6 samples. So if n is the number of samples in full cycle, which is equal to your fs by f naught, for full cycle DFT you do require n samples, whereas for half cycle you do require exactly half number of samples, n by 2. So with this n by 2 samples you can determine the phases. So that's why your equation is now modified into x of k. Instead of n minus 1, now I am going to write it as n by 2 minus 1. So as you have seen already, k represents a harmonic number, n represents the total number of samples in one full cycle. So here I do require only half of the samples. X of n is the data, and n is the value which varies from 0 to n by 2 minus 1. And c is, we already know, if in case we are computing DC component, it is 1 by n. In case of AC or sinusoid components, we take it as 2 by n. Okay. Now, so the half cycle DFT, it is very similar to that of full cycle. The only difference is that here I am going to take, instead of n minus 1, I am going to consider only n by 2 minus 1. Okay. So the same phenomenon. So this is what we have tried. So first of all, we will calculate CW and next SW, and then we multiply it with this one and also with this one, and then we summate those things. So the procedure is very similar. The only difference being the total number of samples which are being considered is only equal to n by 2, but not n. So this is n by 2 minus 1. Okay, but not n minus 1. So Let's take this problem. Now this is the problem which we have already, okay, I think this is a new problem, right? So these are the samples. See how many samples have been given for us? 16 samples have been given for us. Now let us check the input data. See, the signal is having 50 Hz fundamental frequency, which means that F0 is 50. Sampled at 800 Hz sampling frequency, this is Fs. So the total number of samples is Fs by F0, 800 by 50, which is 16 samples per cycle. So all these 16 samples, they will represent one full cycle. So if you want to perform the problem using full cycle based DFT, you do require all the 16 samples. But if you want to do it with 8 samples, then you do require only 8 samples. So with these 8 samples, let us calculate the magnitude of the fundamental component. Okay, so the problem remains the same. So what we are going to do, right? Fundamental component, k is equal to 1. But here n varies from 0 to n by 2 minus 1, right? So that's why I'm taking only up to 7. See, first of all, this is given data and this is given data. And CW, it remains the same, the value. And SW also remains the same. See, and next we multiply these two. And next we multiply these two to get this particular value. And you take the summation of all these three things. So this is the summation of all these data. This is what you have obtained. So it is 3.559 minus say 38.51. Right. For this one, what you will be doing? You are supposed to multiply it with n by 2. Right. Normally here we use it to do it with 2 by n. But here I am considering only n by 2 samples. So that's why I will be taking it as 2 by n by 2. Right. So 2 by 16 by 2, it is somewhere around 4. So if I divide it with 4, this is my value. So this is very closer to 0 minus j10. 10 at an angle of minus 90. So this is the magnitude of that phasor and this is the phase angle. Now if you see, if I use the same data for full cycle DFT, now I am supposed to consider the entire 15 samples. Now I have done the same. This is CW and SW. I have calculated the same. Now this is CW into I and this is SW into I. So I have calculated to see what is the data which I have got here. See, 3.655 minus J78.506. This is 2 by n. Right? Here I am considering all samples. If it was half here, then it would have been n by 2. So this is my data. And since this is also somewhere close to 0 minus J10. So there is no much difference if I consider half wave or full wave. So with just 8 samples, I am now able to compute the fundamental component of the waveform. Now, if you see the comparison of full cycle and half cycle DFT, the accuracy point of view, full cycle is the best one. But whereas in the half cycle based DFT, the response is a bit faster because you are using only half of the samples which you use for full cycle. So the response is faster, but coming to accuracy point of view, full cycle is the best one. And coming to harmonic rejection, half cycle based DFT cannot reject even harmonics, whereas full cycle it can reject both odd and even harmonics also very effectively. So I hope that now you are able to compare both of these things. So coming to the conclusion, both the full cycle and half cycle based DFTs, these are different algorithms, and full cycle DFT is being done for signal over one entire period and takes total number of samples n, whereas half cycle DFT, it considers only half of the samples which are required for full cycle based DFT. So the choice between full cycle and half cycle DFT, it depends upon the specific requirements of the application. So with this, I think you are now able to determine the fundamental components and also the harmonic components using full cycle and also half cycle window based DFT. And this is the problem. Try to solve the problem at the home, and we'll solve more problems in the class. Thank you.